All right, you can see there's a calculus problem behind me. We'll get there. I do feel like on some level I want to address why I'm a little more casual than I typically am for these things. So today happens to be the 13th anniversary of the Virginia Tech shootings. I was there my final year in grad school, so as an act of remembrance, I usually wear something to commemorate the occasion, and the little pin I normally have on wouldn't quite show up in a video. So, okay, that's that. All right. Um, so I wanted to talk about this final section of material. It's going to take us a bit to get at all of the concepts that are going on in here. But I want to come back to remind you about how awesome the fundamental theorem of calculus is. It's amazing. You saw what it did for us in that last section in terms of turning nasty to compute definite integrals into an act of finding an antiderivative and then working out its value at the endpoints of the interval you were interested in. That's great. That means finding antiderivatives is even more important than you might have thought when I first just sort of introduced it as how we go about undoing, derivatives. So let's take a look at this guy right here. So we've got x times x squared plus 1, and then we're cubing, that quadratic that's inside the parentheses. So yeah, you could technically get an antiderivative for this, without having to do anything terribly fancy if you just felt like multiplying x squared plus 1 by itself, 3 times. You could FOIL it once. After that, you would need the distributive property. Then you got to distribute another x. I mean, you could get it, but it's going to be like a big, long polynomial at that point, and it's not going to look terribly pretty. It'd be really nice if we could take this kind of ugly formula and make it less ugly somehow. And that's what the last technique we're going to talk about in Calculus 1 is. It gives us a way to take something and make it prettier. And by prettier, I mean like a formula that we know an antiderivative for from our bestest friend sheet. Okay, our move is going to be to make a clever substitution that cleans everything up for us. So this final section, if you want to refer to it, is called the substitution rule. And you may have noticed, if you look back at the bestest friend sheet, there was one thing on that list of indefinite integral formulas we haven't touched yet. It was in fact the substitution rule. So we're going to see how that plays out in some examples, and then we're going to keep using it as this section rolls to its conclusion. So what could we substitute for in here that would make things the least ugly? That's generally my modus operandi here is pick the thing that cleans this up the most aggressively. So here's what I'm going to go after: that x squared plus 1 inside the parentheses. So if that's gone and gets replaced with just a variable u again, so yeah, that would just leave me u cubed. That's a power function. It's sitting right there on our list of how to get an antiderivative. So that's great. There's one catch. In order to execute this substitution, everything in here needs to be expressed in terms of this new variable u. So you might end up thinking, well, okay, I guess maybe I could do some algebra to figure out what this x is. The real rub is this guy right here, this dx, that notation that I stress a lot that you need to have it at the back of things, but it's really easy to overlook. This is part of our indefinite integral, and we need to convert it in terms of our new variable u. So that's our objective here. And it turns out that's actually also going to end up taking care of this x. So for what it's worth, that d kind of points us in the right direction here because, what's a word we've seen an awful lot this semester that starts with a d? That's right, derivative. So yeah, our move here is going to be to take a derivative of sorts, of this thing. Technically, we're doing what's called calculating a differential, but, you don't need to stress about that for the moment. So we want to produce a du that would, match up with the dx thing that we've got in there. Awesome. So good news, like I said, d is, you can think of the shorthand for derivative here. So if we take the derivative on this side, yeah, that's going to look like 2x. And it's conventional at this point You may recall that Leibniz notation where you might have seen du over dx. It almost looks like I kind of multiplied both sides of the equation by that dx. Don't do that, but that's sort of what it looks like. So this gives us what we're going to end up needing here. Now the catch is, well, we got a dx, right? We got that, check. We have an x. It's kind of out front, but I mean, multiplication commutes, so I can rearrange this like so. I can move the x to the back. So now I've got an x, I got a dx. I don't have a 2. There's a couple of different ways you could approach this. The way I like to do it, just keeping in line with this idea of substituting things, I'm going to rearrange this so I've got something that looks exactly like what's inside that indefinite integral up there. So if I divide both sides of this equation here by 2, that gives me 1/2 du equals x dx. So now I've got exactly what I need. I know what happens to this. I now know what happens to this. That turns into u cubed. This stuff here is 1/2 du. Okay. I'm short on board space. I'm going to erase a bit here to clear this up, but identifying this u and du, as you're going to see, is the key to working out problems of this nature. So bye for now, just to give me a little more real estate so stuff's not too cluttered. Okay, so now the 1/2 is a constant. He can get hauled out front. If you didn't, it's okay. So we've got u cubed du now. And now we can call in our buddy the power rule from our bestest friend sheet. So our exponent is 3. We add 1 to our exponent, divide by our new exponent. You know this drill at this point. So we have 1/2 times 1/4 u to the 4th plus c. All right, so we're almost home. So this is nice and pretty, but there's a catch. Our indefinite integral should be a function of what variable? Yeah, you can see it up there, right? It's x. This is not a function of x. We've got this sort of extra variable u that we introduced, that doesn't necessarily connect. So we need to undo our substitution at this point. Anywhere we see a u, that thing we substituted for u needs to go back in, i.e. this x squared plus 1. So 1/2 times 1/4 is 1/8. I mean, if you'd written them separately, I wouldn't hold it against you, but it looks a little nicer this way. And that looks an awful lot cleaner to my mind than what would have happened if I had pounded through the algebra here to work out what that cube would be and distributed in x and then just treated it like a big massive polynomial. So that's that. This also may answer a question that's kind of been floating around in the back of your head for a while here, like, why do all the bestest friend indefinite integral formulas talk about u instead of x? This is why, because the substitution rule gives us a way to get at a lot of these things without necessarily having to jump through those same, hoops. It's kind of an analog of our friend the chain rule. You may recall when we talked about derivatives, I stressed really heavily how important the chain rule was and how many doors it opened for us, how many locks it picked, so to speak, in terms of finding derivatives of stuff. The substitution rule basically lives in that same place. It's if you actually kind of scrape some of the the integral notation off it, you'll notice it looks an awful lot like the chain rule formula from the other side of your bestest friend sheet. So here's one example. We're going to take a look at some more, but I think we'll go ahead and kick that off in another video. You will find inside our Moodle course, I have uploaded a worksheet that kind of breaks this down in a manner strikingly similar to what we did when it came to derivatives with the chain rule. So go ahead, pop that sucker open, and then start up the next video, and we can take a look at some of those examples.